Yes. Andrea, thank you. So sorry again for the problem with the internet. I hope that without the video it will be okay during for the talk at least. And thanks to Pedro for helping with the slides. And so I'd like to talk about some work in progress that we are doing with Lance, Yu-Ting Liu, and Georgios Papathanasiou, which is related to calculating scattering amplitudes exactly at particular point in the kinematical space in n equals 4 superior limits. So this is a follow-up of something we've done a year ago for the 6-point amplitude. And I would like to, what we are doing now and hope to finish soon is to try to generalize this story to higher point amplitude and see if some nice integrability structure are emerging. And we think we found some nice structure which are perhaps not yet entirely cleaned up, but inspiring. So I will probably try to be fast on the very first slide. It's just recalling this nice duality that we have between scattering amplitude in this theory, gluon scattering amplitude in this theory, and null polygonal Wilson loop, and which, as you know, arise kinematically at least just by taking the momenta of the incoming gluons and putting them one after the other and forming this way some null contour, which we use as a contour to define the Wilson loop, vacuum expectation value of a Wilson loop. So it's not something that one should expect to be true in general. It's not something that is true in other theories, and probably not even in this theory if we go away from the planar limit, but it is expected to hold at any value of the coupling in this theory and for any number of gluons. And there are also generalization to situation where we do not scatter gluons, but scalars and fermions and so on, which I won't talk about today. It's sort of going to be about pure glue. And so this equality is also sometimes seen as a sort of embodiment of integrability. Okay, and it does a lot for us in the sense that it fixes 4 and 5 gluon amplitude, for instance, and forces the remaining one, which are the one I will be discussing today, like for 6 or higher number of gluons, to be function only of the cross ratio that we can form out of the Mandelstam invariant or distances between the cusp in the figure. Okay, so that's a huge restriction if you think about it. And the goal, of course, is to try to determine as accurately as we can this object as function of the coupling and of the many cross ratios that we have. And for the simplest case, which is n equals 6, we have 3 of them, 3 cross ratio plus the coupling. So that observation is at the basis of most of the techniques we have in this theory for calculating efficiently scattering amplitude in this theory, like the amplitude function Bootstrap, for instance, that Lance developed with his collaborator, or the also the calculation of strong couplings that use TBA, which I'm mentioning because we will be using it later on, and also some more sophisticated or fancy technique like the pentagonopy, which aims at constructing scattering amplitude in particular at finite capping, but starting from particular corner, like the collinear limit. So the hope is to solve for scattering amplitude as generically as we can, possibly plot something if that is plottable. But of course, whatever the starting point, resumming perturbation theory is hard, and resumming kinematical expansion is also hard. So well, we do our best, we try our best. But so one of the ideas that's often used is to instead try to look at scattering amplitude close to particular point, like at some boundary of some region. So you can define some region you like more than another and look at particular point where the amplitude might develop some singular behavior or just trivialize, like in the collinear limit and so on. And it's also a start of pathway to solving scattering amplitude in general, we believe, because if we have them under control at the boundary of a domain, we might possibly be able to solve for the amplitude inside, in the bulk of this domain, like in the spirit of what people are doing at like Pedro and collaborator in other situations. like using other technique like unitarity and so on. But that's an idea. And in any case, if we cannot control things at the boundary, we probably should not hope to solve anything elsewhere. And this is where integrability usually reveals itself and appears to be the most tractable, like I said before, in the collinear limit, where we have this leading twist OP expansion that fixes the amplitude for us, or some other version of this collinear limit that resum partially the pentagon OP series, or yet another form of it, which is BFK. Someone is talking? No. So what I want to talk about today are some special limits, which we call origins. Well, there are special points to begin with, but we will see that there is more than just point in this story, where we believe integrability will play a role, and which is not just inside the collinear limit or something that was already known before. It's actually not infinitely far away from the OP, but still, it is at a distance where you actually have to resum a lot of stuff in the OP series. So it's not a different form of integrability, but it's probing definitely some different corner of it. And that's a limit where we take a lot of Mandelstam invariant or cross ratios, actually a large, probably the largest number we can, simultaneously to 0. Okay, so it's a light like limit of sort of the type people have studied for correlation function, for instance, except that here we try to really maximize the number of Mandelstam invariants that we are sending to 0 in the first step. Of course, eventually one may try to relax this condition and so on. And what has been seen is that amplitudes develop some large logarithm in this regime, so something that is akin to Sudakov behavior, if you're familiar with that, with at every loop 2 more power of a logarithm appearing. And what is nice is that this behavior exponentiate eventually, such that calculating the amplitude in this limit amount to trying to determine some quadratic form in logarithm of the cross ratio. Okay. And well, in this talk, I try to explain and explore with you this behavior as exactly as we can in the coupling for a generic number of gluons. So I will first remind you of the 6 gluon origin, which is what we did and was motivation for going ahead. So the conjecture that was first formulated by Lance and collaborator is that the MHV 6 gluon amplitude admits this Gaussian behavior in the log of the cross ratio that I've just mentioned near this origin. So where here we have 3 cross ratios for the hexagon, and we send them both, all of them to 0 simultaneously. And if you like picture, it corresponds to taking this hexagon here and trying to flatten it along 3 corners at the same time. So as if we were getting a null triangle at the end. Okay, so we are making the distance 1, 2 to be 0, and 3, 4, and so on simultaneously. And what we are finding is that the amplitude can be written in this very concise way. So there are essentially 2 cyclic symmetric polynomial, quadratic polynomial in the cross ratio that one might write down, which are given here explicitly. And we have in front 2 coefficients, which are a priori function of the coupling, and which I'm labeling here with some parameter alpha, which are set to 0 in one case and 2 pi over 3 in the other case. So of course, it looks trivial once you make the assumption that there is such a behavior to write such an ansatz, but in general, we don't know why this behavior is there. Why is it only 2 power of the log coming out at each loop? Why is it exponentiating? Blah blah blah. We don't really understand very well. It's one of the big questions we'd like to understand, but well, in lack of good idea for understanding, we may just calculate things. So and yeah, just some technical comment. It all as written here for suitably defined amplitude. So amplitude of gluons and so on, they are not well defined, as you know. They are infrared divergences, we need regulators, and so on. And so we have to subtract it. But there are some nice ways of doing it, and there is one in particular that preserves cyclic symmetry and so on. And here I'm giving you a table of the values that one finds through 7 loops. I just put 5 loops because 6 and 7 loop expression are huge. Well, bigger, actually too big for the slides. And and what you can see here, so sorry, I'm using some old terminology. So this gamma oct is gamma alpha is equal to 0, and gamma hex is gamma alpha is equal to pi/3. And in the middle, I'm putting gamma cusp, which everyone should have heard about at least once, which is this quantity that control infrared behavior of scattering amplitude in any theory. It's not just n=4, but we know it very well in n=4 as a comparison. And what you see if you compare this number is that they are all very much related to each other. And what we've understood is that they are all actually partners or friends. And can be encoded in a single object that we call the tilted cusp anomalous dimension, which is on the next slide. So what one can do very easily as a check is verify that all these quantities that I've shown you actually indeed follow from a trigonometric deformation of the cusp anomalous dimension. So in a way, we are injecting some angle alpha or some cos alpha inside the perturbative series of the cusp, such as to fit what we have. Of course, we are not doing it randomly. We had some idea about how to proceed, and another way of understanding it is by deforming or tilting the BES kernel that is controlling the cusp anomalous dimension in this theory to all loop. Thanks to integrability.
Yeah. Is it like similar to introducing a mob number into kind of folded string, or like the fractional number of folds, roughly speaking? You know what I mean?
I don't think so, because this, if you do that, strong coupling is only just a rescaling of the coupling, no?
Or... Yeah, probably.
It's a more complicated deformation of strong coupling, for instance, so I will not expect it to be that simple, but I cannot exclude that there is a limit where it reduces to that. So,
but at strong coupling, do you know what it kind of what you should do with fold string to?
No, that's actually a very good question. So what exactly is that object? Is it a real object or not? Is it just some, obviously something we introduced because we wanted to fit some data, or actually it's not the way we found it, but anyway, it's a way of understanding it. And but it's not clear whether this object has exists on its own, like the cusp exists on its own in a way. So we don't know if it is associated to something else, but that's one of the big questions I guess we like to understand. But here I just wanted to emphasize the fact that this is an object that we that I'm not going to talk so much about later on. Well, it will of course be with us all the time, but because we believe we understand it. Okay, we just we do this modification of the kernel. So if you are familiar with the kernel, you recognize the overlap of Bessel function. We do this modification, and then we just know we can calculate things. If we need it at 10 loops, we calculate at 10 loops. If we need it at strong coupling, we solve this. We invert this matrix, infinite dimensional matrix, at strong coupling, and we read off the answer. Okay. So on the next slide, actually, I'm showing, I'm flashing a plot, okay, just to show how things look like for the 3 values that I've mentioned so far, which are in the middle the cusp, and then these 2 other guys, which we need for the, okay. So we have good control on that. So, well, the big question I've mentioned already, we don't know why it's exponentiating. We don't know why it's quadratic in the logs. We'd like to know. We don't know if we can give independent meaning to coefficients, but we can try to explore again if the original this phenomenon is, and there is actually a lot of data we can play with, or techniques we can apply that will tell us if it can extend or not. And what we're going to immediately see is that the behavior does not apply to an MHV amplitude. So we are not going to explore that direction of trying to put scalars and fermions and so on. It looks like it's not helping. But we can stay with MHV and move to more gluons, higher polygons. Okay, that's what we will do. And there we already have some data from Lance and Yu-Ting about the 7-point amplitude, which was found also to have this logarithmic behavior in a limit where we set a maximal number of cross ratios to 0. So for the 7 gluon amplitude, we have a priorized 7 cross ratios, like 1 for each cusp, roughly speaking. But there is a Graham constraint. There are only 6 independent cross ratio. The other one is fixed by again some algebraic relation that among distances and blah blah blah. And what one can see is that it's not possible to set them all to 0 simultaneously. The maximum you can do is to set 6 of them to 0, and the last one will go to 1. Okay, so that's the kind of thing we'll have to accept and play with later on when going to higher point, which is that we cannot just set all cross ratios to 0. It's not reasonable, but we try to maximize things. Okay. And what was observed, I'm giving here the result at 2 loops for the remainder function, is that it's again nicely quadratic. Okay, in the logs. Of course, it's a bit less symmetrical than before because we don't have the freedom of shifting 1 to 7 and so on anymore. So it's certainly a more complicated problem to solve for, but still there is some simplification, and there is some evidence that the structure is stabilizing at 4 loops because Lance and Andy, they did the calculation through 4 loops, I believe. So we can see that only 3 polynomials are needed, for instance, to write down the full 4 loops expression. And each one will come with some coefficient in front that will like to map in some way to this tilted cusp, or this deformation of the cusp that we had found before. Okay. But one thing we can say immediately is that we cannot just use the same angles as for the hexagon. It isn't working. There is no way we can do that. And also in general, it's not an easy game to play. You could say just change the angle, but this tilted cusp has this tendency of producing trigonometric numbers, which are rarely rational, as you know. Well, it depends on alpha, obviously, but we are not thinking about taking some crazy alpha either. So so very quickly it gets complicated, and because the answer must have rational coefficients. So that's already a hint that we should average over some angles which form particular family and so on. But anyway. So the marginal conjecture, of course, that we will be exploring is not just about 7-point, but in general is that MHV amplitude should have this Gaussian behavior, like that we can write as a sum of this gamma alpha again times some polynomial with for some alphas. Okay, that's what we want to make sense of. That's what we want to test near some point in kinematics. I mean, in some limit in which we expect a large number of vanishing cross ratios vanishing. Otherwise, it will most likely not be that simple, which we have to determine as well. We don't know where we should look. We don't know the quadratic polynomials either. We don't know the angles. We know nothing, but we have hope that we can do something. And in this talk, I will explain, in fact, how to get some very important insight about all of this information, like the angle, the polynomial, and their pairing using string theory. So we use a lot perturbation theory at perturbation theory for 6-point. It was essentially everything we've done, but it will prove more useful to use a string theory for higher points. and then in part 2, if I will have time, I will explore how many origins there are, and some more global aspect of the problem, I would say. Okay.
Could you
So
remind
the plan,
what is the?
That was all about.
Sorry. Could you remind what is the meaning of this angle?
We don't have any meaning of it since we introduce it as a kind of deformation of sort of BS kernel. Okay. So it is a bit as if, I don't think it's identical, but it's a bit as a sort, if you were doing some sort of Q deformation by hand in some problem without knowing whether it comes from deforming some algebra or something. So we don't know what it is. We just found it interesting to do it and useful.
And in your case, it takes some nice values always, like pi over the natural number.
You have to define natural, but yeah, there will be natural.
I mean, the rational multiple of pi.
Yes, there will be a rational in all situations I will be talking about. Yeah, we will see actually how this angle is popping up of coming out of the string theory. Well, it's not truly the string theory. We are helping the string theory to a bit. Okay, so this is the plan. Okay, so so part one is for the first part of the talk, which is already behind us, I guess. Okay, so let's get started. So yeah, a few words about why string theory. So it's very natural to look at string theory because we look for something that is exponentiated. That's something that we get automatically in the string theory, as you all know. We get that the answer is the exponential of the area of a minimal surface in ADS that is ending on the contour that we're interested in. And of course, in string theory, this phenomenon is driven by the strength of the coupling, the string tension, G or root lambda, which is getting very large. So that is killing the fluctuation, as we know. And here, in general, we don't expect to be in such situation where the string tension or the gamma, in our case, the coefficients are large. But on the other hand, we have the logarithm that are large. So it's a bit as if, you know, we could still be using string theory reliably here. And as we will see, in fact, it will be extremely easy to promote things to finite coupling once we know how to calculate them in the string theory. In a sense, it is.
Yes, in this limit, MHV, non-MHV doesn't matter, right?
Yeah, in this limit, it does not matter. You're entirely right. So it could actually be that what we are calculating now is something you also want to subtract in the case of NMHV. But I don't remember very well. But I think the problem is that it's not so much leading either. It's not the most interesting phenomenon for NMHV. So you can subtract it, but you will still have to resum something non-trivial. So I don't remember. We should discuss with Lance during the break. Okay, so string theory will, in a sense, resolve these kinematics and these polynomials for us efficiently. So now this is the tough part, the TBAs. So this is where we start calculating things. So I just wanted to remind you that there is a way of solving the problem of minimal surfaces in ADS, or actually the area of the minimal surface in ADS, by using TBA equations. Okay, so I wrote them down here. So if you know TBA, you will recognize a few things. Otherwise, you won't learn anything. But they are akin to equations for system at finite temperature, chemical potential, and so on. Except that here we don't really think along this line, although there is such an interpretation, but it's not essential. And there is no actual temperature. It's zero temperature ideal space and so on. But we have this phi, tau, and sigma, which are the external parameter, which arises from the geometry. Okay, so in a way, they are measuring how far, how complicated the geometry of the loop is. In the case at hand, the hexagon. Okay, 6 gluon. Okay. One thing I should perhaps mention for those who are familiar with the system of equation as written in the original paper is the fact that this is not boost invariant. So it's an alternative way of writing the equation that were originally written by the gentleman up there, which has the advantage that phi, tau, and sigma here have a transparent meaning. Okay, so they are directly associated to a particular parameterization of the cross ratios, U1, U2, U3, which is known as the OP coordinate. Okay, so sigma, tau, and phi. And in particular, when we send tau to infinity, which is what we will call the zero temperature limit usually for the TBA, We are in the regime, of course, where the y function are all very small, so the system can be iterated. We are in this collinear limit or OP regime where we have control typically, and we have control because we can iterate. That's the idea behind it. Okay. So now for the regime we are interested in, where all cross ratios are going to 0, we should not only take tau to be large to kill U2, but we should also send phi to infinity to move off of this line U1 plus U3 equals to 1 that we were landing on otherwise. And besides, we have to take phi to be also bigger than tau in a certain way to get something out of the equation. And what do we expect here? Well, we do expect some sort of simplification, because we expect that okay, tau is very large, it means 0 temperature. Phi is very large, it means large chemical potential. So we expect to form a Fermi sea and to see some excitation condensing, and which excitation should condense precisely those that are charged with respect to this chemical potential, with a maximal charge to mass ratios and so on, the usual story. So in our case, it means taking y1 to be very large, and the other y's, we have 3 y's, to the other 2 y's to be 0. Okay, so we can still totally ignore part of the TBA, and the other one we linearize. Okay, there's something that is very well known. There are many people that have been doing that before us. There is nothing new, and there was actually a group of people, Sato and collaborators, that did it with a very similar problem in mind. It's a bit different, but it's related to. So, and well, now the good point about this equation is that it is, of course, way simpler to solve than the original TBA. We just do Fourier transform and we get.
Excuse me, Benjamin.
Yeah.
David is speaking. May I ask you? So you expect that you don't expect any boundary, any Fermi rapidity fix. So the integral goes from minus infinity to plus infinity.
Yeah, that's a very good question. Well, in general,
because usually you have the Fermi rapidity, yeah, but not always. It depends, yeah, a little bit on your limits, yes.
Yeah, so that's something, that's a very good point. So so for instance, if sigma here is 0 or purely imaginary, I guess we could still assume that we are solving something real, which is defined over some domain. And then we'll have this Fermi rapidity, which as we augment this Fermi rapidity, we will move away from the OPE and slowly move to the origin. Okay, and you're right that in principle, to solve in the way we are going to solve, which is the easy way, we aren't going to make anything complicated here, is we need the full line. And to tell the truth, we don't really know what are the precise conditions that we should have on the geometry to make this approximation reliable. So that's a limitation. But I will comment a little bit on it later on. But you're right that in principle, it is not possible to have the y function being large everywhere.
Mm-hmm.
So
thank you very much indeed.
Thanks for the question. And so the solution is simple, as you can see, and I wrote it here in a z variable, which is exponential of some variable t dual to theta, because everything is rational then, and you start seeing some natural angle coming out of roots of unity and so on. Okay. So now for the minimal area, it's also relatively straightforward. We have a beautiful formula that was worked out by Pedro and collaborators that gives this area in terms of some Roger dialog, or maybe it's not Roger dialog, but in terms of dialog of y functions, and the source IA, which is what is standing, the driving term of the TBA, sorry. And here again, if the y function are small, we can ignore. And if they are large, we linearize. Or to be precise, we get something quadratic. Okay. In the case at hand, the only thing that will remain is something like log y times log I. That's what we have to integrate. Okay. And in Fourier space, it's straightforward, and we can write this closed form, this closed expression for the area as the integral of something that we like to call the string integram, which is quadratic in the cross ratios, almost by construction, because it's quadratic in the driving term, and so in in the OPE parameters, and which is otherwise rational in the Z. Okay, that's the very bottom equation on this slide. Okay. So what do we do with that? Well, we could just use it to calculate the area and compare with the all-order conjecture that we had before. Or we could manipulate it to try to find a way to also modify it to get some more complicated coupling dependence. This is what we've done, and there is a useful trick here, which is essentially...
So why do you keep it as an integral? Can't you just compute it?
Yeah, so for instance, a useful way of calculating it is to deform the contour. It's something rational. Okay, so if you okay, I'm explaining to the other people. I'm sure you already done that in your head, Kolya. It's standard Russian trick, I guess. But you have something rational, so you can write it as a contour integral with a log, as if it was integrated along the cut of the log of your string integral. And this way you can localize the integral on the roots of your integrand. Okay, which in the case at hand are just roots of unity, z equals to -1 or I, or some roots of third root of -1, something like that. Okay. And if you do so, you immediately get the answer in the form that we like, which is as the sum of roots or angles here times a polynomial, which is also labeled by alpha, and which will take different form for different value of alpha. So when alpha is 0, for instance, it's just the log of the product, and if alpha is pi/3, it's some more fancy combination, okay, which would still be cyclic here in the case at hand for this root, but might not be also depending on the value of the root. Okay. And we see that it matches all order formula just by plugging the expression for the strong coupling limit of this tilted cusp that we have. Okay, so it's just this expression where you can see, Kolya, that it's not quite the same. Well, not obviously related to rescaling of lambda. But the reason we like this trick here is not so much that, well, we were not really aiming at calculating it, we knew the answer, but it's immediate. When you see this form, you want to modify it or uplift it to get the all-order formula just by replacing the log in the integral by whatever you want. So that's what is explained on the next slide, which is here, which is essentially the key message for today, which is that we can represent, that's a totally equivalent formulation of what we had at the beginning. We can represent our result in this contour integral form, where we are essentially convoluting or multiplying whatever the string integrand from the TBA, which has no coupling dependence, just kinematics in it, and this function of the coupling that we can think of as an effective coupling of sort G, which to match our formula should be such that when you evaluate it on a root of unity, reduces to this tilted cusp. Okay, and this is just, I mean.
Okay, question. So in terms of the surface, I don't know to which extent you can recover it, but if you could recover it, what will it give in this kinematics, or what's interpretation of the different?
I cannot.
Will it be?
Well, I can't tell, because reconstructing the surface is a more complicated problem. You have to go back to the origin of this. Yeah, you have to go back to, yeah, no, I cannot tell. I don't know exactly what the surface look like in this limit, if this is a question, and whether we can understand this simplification from the surface viewpoint or not.
But then if we speculate these different residues, will they correspond to what, some disconnected parts of the surface, or is there any intuition?
If I had to speculate, I don't know. It's a Fourier analysis. Why? Maybe it's in the spirit of this wavy line approximation. I don't know, some Fourier analysis. I can't really tell. It's not very clear to me. I just, at the moment, it's a formula. You know, you try to see the string behind it. It's hard. But the claim is that it's fully equivalent to what we had before. But we get something more, I believe. We get that we now understand where these polynomials are coming from, and as well as these angles alpha. They come from this string integrand in a way. So give me a string integrand, I give you a formula. That's the idea. Well, there is, of course, some interpretation we'd like to associate to it, but this is, of course, very speculative. We could maybe think that if this formula is not just a recipe or
so can you like summarize the notation? So you had TBA in U, and then Z was Fourier, literally Fourier in U, or?
Oh yes, sorry.
local.
Yeah, sorry. I'm being a bit fast. So Z is a dual, is a Fourier transform of theta.
So it's log of Z is a kind of momentum variable, right?
Yes, log of Z is a momentum to theta. Theta itself was the spectral parameter of the that you get for free at strong coupling.
Theta was in whatever it's in TBA. Yeah.
Yes, it was in TBA. So yeah, theta was in TBA. Log Z is a momentum of theta, and S is related to the density of area in this Fourier space. Okay. Yep. So in interpretation that we could try to make about it is that perhaps, you know, the string saddle point localizes and on this particular classical saddle, and that the only thing that is happening is a renormalization of this string tension that injects this G of Z. But okay, in practice, we have no idea how this is happening. Maybe it's just a red herring. But anyway, if you want to recover the string, you just plug the strong coupling asymptotic for G of Z, which we take from the asymptotic of gamma alpha, and you're back to what we had. So this is in principle guaranteed to work. There is a few subtlety about the contour, which I will just mention very briefly, so that we can use different contour depending on whether we are strong or at weak coupling. And that is motivated by the fact that there are some singularities that are moving around from G, and that opens sometimes some path where we can essentially write this contour integral as a residue around 0, which is extremely convenient at weak coupling, or that forces us to deform the contour to the real axis like a strong coupling. So that's just a comment about the fact that different values of the coupling typically correspond to different choice of contour for the convenience.
Ben, if at some point
and the last slide before the break, yeah.
Okay.
Yeah, this is time for break. That's what you're saying?
No, just like start thinking about it. Yeah.
Oh yeah. No, I'm thinking about it because it's where I wanted to break. So the next slide is so it's just a comment for David's question about the when is it exactly this approximation valid. So it's also a comment about what do we expect to get after the logs. We get some double logs, but after that we expect, at least at weak coupling, we expect to get a constant up to power suppression, power suppressed term. But in string theory, it's most likely true that it's more complicated than that. We may still have a constant. We do expect a constant, but well, string theory is not very good at capturing it properly, it seems. But more importantly, it's not entirely clear to us how big are the correction in general when we are strong coupling. And the difficulty is directly related to this assumption about when exactly the Y function is large, when can we exactly, you know, use Fourier over the entire axis to solve, and when are we just wrong about it. There is definitely a situation where we know the answer.
Why can't you just plot it? Why can't you just solve it numerically and check?
No. So you can solve numerically. It's a bit at least in the case of the 6. Sorry, for the hexagon you can do. For more polygon, I'm not so sure about how to proceed. In the case at hand, I don't think it is so much needed to solve numerically, but at least what I wanted to say, that we do expect things to get more complicated in general. And when the y function are constant, of course, it's straightforward to answer this question. I mean, if it is constant, if it is big at one point, it is big everywhere. But that is only when we are in this situation where u1 is equal to u2 is equal to u3. That's a very particular case. Whereas in general, the solution that we have found by linearizing and so on, and Fourier transforming on the real axis is the one I just wrote. Okay, so in fact, we are just calculating some trigonometric function, some sinh hyperbolic function, cosh hyperbolic function, with some with some periodicity. And what I want to say that most likely the assumption that the y function is large is going to be true if the first coefficient is big and the remaining one are not too big either. Okay, so the first coefficient being big means the constant part of the y function is big, which is going to be so if u1, u2, u3 are small. But on the other hand, we don't want the cosh and sinh that are following to be coming with a large coefficient, because that will mean that we start with something big, but very quickly it may be changing sign and so on. So the idea will be that at strong coupling we have to be more we might have to have extra constraint on like sending all the cross ratio to 0 at the same speed, okay, to be in the regime of validity. So of this approximation. Okay, I think we can stop here.
All right, thank you. So Andrea, the German? No, anyway, so we have a coffee break for what, 10 minutes?
Yeah, let's, well, maybe let's make 10 minutes.
And then I have like 20 minutes. That's the deal.
Well, yeah, roughly. Yeah.
Okay. Ignition. Okay. So now I will generalize, of course, to NEN, because this formula is calling for that, and you should not move in that direction. And that was just recalling the previous one. So again, the only thing we are doing now is to put the subscript n everywhere. Okay, so the idea is that if we can find this, repeat the analysis for higher n, then we will get some very natural conjecture on that for higher polygons. Okay, that will be parameterized by this tilted gamma and so on that we like. Okay. So how do we get now this S of n? Well, we just repeat the analysis with higher TBAs. That's the next slide. So in general, we have this system of equations that was worked out by Pedro and Amit and Franz, which is built on a Y system, that's for the expert, which is of A3 times AN minus 5 type. Okay, it's actually not exactly this system. There is a, I think people call it a braiding or whatever, but it's closely related to it. And so we have as many Y functions to solve for that we have point in this grid. Okay, and we have equally as many parameters that are parameterizing the geometry. These are this triplet of phi, tau, and sigma, and there is one for each. Anyway, there is n minus 5 of them. So the most nice thing we can do, and what we are doing as a way of approaching new origins or new limit where we expect things to simplify, is to take again this limit of large chemical potential and time, tau, with the chemical potential again being much bigger than the time to get some large Fermi C. And what we have as a new freedom, of course, is to send the phi differently to infinity. We can sometimes decide to excite particle with positive charge in one channel and then particle of negative charge in another channel. So we have a kind of signature we can use to explore a bit of this eventually moduli or space of origin that we will find. So here's an example for the.
Can I ask a quick question? So these variables, I thought, were very convenient if you are close to the OP, right? So you have a sequence. Things are not symmetric at all, right? So you have
yes
this sequence. But in your kind of pictures, at least for the hexagon, things were very symmetric, right? You had this triangle inside the hexagon, and now I would imagine for higher polygons to have some similar shapes, right?
Yes.
So they don't look very OP friendly, but this definition is very OP friendly.
So this definition is very OP friendly, and what we are going to find is not symmetric at all. So before we
and then there will be other origins that are not OP friendly to restore this symmetry, I guess.
And yeah, you're right. Of course, there will be images. Yes, okay. Right. Yeah, yeah. You already know too much, I believe. But yes, what we are going to find is not as nice and symmetrical than what we had for the hexagon. Yes. For the octagon, for instance, for 8 gluons, we get these 3 possibilities. So there is an overall sign that we don't care about. It's a symmetry of the problem, where we can excite, gluons of the same type or different type, one after the other. Okay. With blue meaning large, of course. So, well, the rest of the analysis is the same as before. It's just higher dimensional. So we are dealing with matrices and so on, and vectors. And we are making exactly the same assumption as before. We have even less evidence that they are correct, but it's a working assumption that we can work on the entire line and so on, and just Fourier transform. So we just have to deal with some complicated kernels. Well, not that complicated, but which are matrices, invert them, and so on. Okay. And everything, all the ingredients look very similar to each other, like there are similarity transformation and so on. Nonetheless, I mean, different signature, if we excite differently, there are relations among these objects. But as we will see, they map to different limits. So in terms of cross ratios, they do map to different points. And so we find it useful to keep this information about the signature and so on as much as we could to explore and to get some insight about what we are supposed to find.
Where were these epsilons defined that are here?
Well, these are the sign of the phi's. So
the signs of the phi. Sorry. Yeah, if I don't, if you allow me.
Yeah.
I see.
And now the general structure, which is on the next slide, which is that is the piece that is very much independent on the signature, and in particular the angles. They only depend on n here. So we have this string integrand that we can write in general for any n, where you start seeing the roots of unity appearing from this factor exactly. And then there is some polynomial in the numerator, which has a certain degree and certain property, and which is quadratic in the OPE coordinates, which mean quadratic in the log of the cross ratios, and which has all this information about the kinematics. There is a simplification as well if we go actually on shell. So if we evaluate the integral close to the roots, to the pole, we find that this polynomial, which is typically a mess, factorizes. So it takes the form, it becomes the module of something, some Q, okay, which is simpler. Okay, that's an observation we could make. So the example for the Eptagon, we have these 2 possible saddles with a side flip or with no flip. And in both situations, the angles are the same. We find that they are given as written here. So there are 6 of them. Of course, alpha goes to minus alpha is always a symmetry. So we can just say we have 3 of them. And you see they are quite funny, divided by 18 and so on. It's they have slightly different Qs, and also they map to slightly different geometry. So in both situations, we do have that 6 quantity are sent to 0. That's naive counting we would expect in this limit is to have like 3 times n minus 5 quantity going to 0. 4 of them are cross ratios. So, okay, they go to 0. And the other 2, they are product of cross ratios, okay? And so to disentangle, which one is actually going to 0 in this situation, is it 7 or 3, blah, blah, blah. We must look at the rest of the information, which is coming from the Graham constraint, which become pretty simple in this limit. and which is telling us that there is two geometry we should expect, one in which the remaining cross ratio U7 is 1, and the other one where it is a line between 3 and 4. It is what we should expect. And the two factors are realized by the two possibilities that we have, like this plus plus or this minus plus. Okay, these are the two options, and they are both realized here in realizing this constraint. Okay, so what it means is that in one case we are just back to the origin that we had before, and we were studying that Lance studied, with U1 to U6 being to 0 and U7 being 1. But the second case is more interesting because we are not getting just one point, we are getting a line that is connecting two images of this point. Okay, so two cyclic images of this point.
Sorry, Ben, a small question. So in this case, you could just plug the twisters that correspond to the Eptagon in all this U1 up to U7 and see what they do, right?
Yes, yes.
You don't need to use this gram determinant, blah, 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 right?
Oh, no, no, you don't. You don't. You can do that, yes.
Okay.
But you always have to be careful. Yeah, you can. It's just, okay, it's another way of presenting things, but yeah, you can just plug the twisters and calculate. Okay, but that's okay. That's a novelty here. We are learning that we don't always get a point. Sometimes we get also line between points. Okay, so we start emerging some bigger structure. That's we see emerging some bigger structure. And we can run a check at for loops as well. So now that we have, yeah, everything was inspired from string theory. So you could say, why should I trust it? Well, so we can just take the expression, like I'm giving here the expression for this Q, which was inside the module square on shell, in the case of plus plus, which is just simpler. And as you can see, it is nice. The expression is as nice as what we had before for the hexagon, but it's less symmetric because, of course, we are not summing over the roots, the 7th roots of unity, and we don't have the 7 cross ratios. So it's not a symmetric polynomial. But still, it's a relatively gentle polynomial. You can just plug the expression for this gamma alpha and get the answer. And you can also check that the Gaussian behavior that we were finding between the 2 points, between two origin, two copy on this line, is effectively there as well in the perturbative data at for loops. Okay, so you can do all the check, and so that's a confirmation that what we are doing is correct. Depending on how much time I have, I forgot when we started. Yeah, Andrea, how much time do I have?
How much do you have until the end? How much do you need?
Well, okay, I'm going to skip the OPE.
But yeah, I think 10 minutes. If
yeah, 10 minutes will be enough for the end, but not for the OPE, I think. So I will skip the OPE. These are structural check. It's interesting, but I prefer to now go to something lighter, perhaps, which is about getting some more global picture and trying to see, you know, from farther away what we are getting. So in general, what we will do is that for each polygon, we will introduce the basis of cross ratios. But the more natural way of doing is to start with these U's that everybody knows, and then going to the V's, which are built out of next to nearest neighbor distances and so on. And we can keep doing until we exhaust it. We went from one side of the polygon to the other. Of course, they are not always independent because of this gram constraint again, and we know that only 3 and minus 15 of them are independent. But it's nice to work with all of them anyway, because otherwise we have to solve constraint and so on, which most of the time means going to different parameterization. Okay, so either OP coordinate or clusters coordinate or whatever. Okay, twisters, which are sometimes nicer, but not always. And so the idea is that we are essentially trying to look for points that we will find by taking this limit of the TBA, that we will always be in such situation where we get a large number of cross ratios that vanish, with large meaning at least 3 and minus 15, but possibly more if that is allowed also. So what we could do is just try to classify the option. Like for the hexagon, for instance, there is obviously only one solution. For the heptagon, it is a bit more complicated because we have to look at the gram. But if we look at the gram, we find that there is actually only one solution, which is the one we had before, up to cyclic images. And for the octagon, it's more interesting. Okay, so for the octagon, there are many more options, and we can essentially list them in a table.
So now I'm a bit confused. I think before you were stressing something that it was not a point, it was a line, but here 7 is still a point, right?
Oh,
or am
yeah,
I confusing things?
Okay, sorry. At the moment, I'm classifying points. And here I'm saying I'm taking a different viewpoint, and I'm just trying to classify points. Okay, what I call origin here is just a point. And then later on, we'll try to see if we can also have like line between points and so on.
Connect them, I see.
Okay, yeah. So on the next slide, we are listing what we have found for the octagon. So again, to be clear, you play the game, you write all the grams, and you start setting as many cross ratio to 0 as you can, and you see what are the options. Okay. And here we play this game with, you know, from either 9 or 10 vanishing cross ratios. 9 being what we would expect to be generically obtained through our construction, 10 being a kind of bonus in a way, something something else actually. And so we found that there are essentially that there are just 10 possibilities. So the first one in the table, O1, has 10 vanishing cross ratios. All the U vanish, but also 2 V's. And all the remaining one have 9 of them vanishing. Okay, but sometimes, you know, we get some V's which are 1. Sometimes we get U's and so on. And if we, so these are target for us. We will expect all these points to be on the same footing and possibly be such that if you calculate the amplitude at this point, you will find some quadratic behavior. Yes. So the TBA analysis that we run gave us only 6 of them. Okay, and so clearly something is missing, and it wasn't immediately clear to us whether the other one were special or not. Okay, so that's so to shed light on this, we added connection. So we did what Pedro was asking about. So we added connection among these points by using some cluster algebraic techniques, which I will not explain, and we get this kind of nice rosace. Okay, where
can I ask a question?
Sure.
Why TBA at the technical level, why TBA doesn't give access to all of the origins?
Well, so I don't know if it is, so, okay, there are 2 things. So first, it could be that one of these origins, for instance, are too far away, such that they are actually, for instance, sometimes people distinguish between the positive domain and the non-positive domain, which may or may not be covered, for instance, by the OP coordinates, or might necessitate some very complicated continuation that no one knows how to do, for instance. I'm not saying it is the case, but one could imagine a situation where just points are just too far away from where you define things. Then when I say it's not captured by TBA, I should be more careful. It's not captured by our analysis. So we take the TBA, we linearize them in a particular way. We get this freedom of, you know, sometimes exciting one node and sometimes another. But that's the only game that we've played. And it might be that there are other saddles that we can just take into account and that will accommodate for these origins. We are just not very confident about it.
Let me maybe just add a comment that typically you get a TBA that converges in some region of some cross ratios. And then you have to analytically continue. And by doing that, you pick extra terms. It's like these excited states in TBA business.
Yeah.
So you could first analytically continue and then try to go to these other origins, I guess, right?
Possibly, yes. I don't know how feasible this is. In principle, I agree with you that you should be capable of, perhaps that was a short answer, sorry, to Kostya's question, which is in principle, you can do everything, but the cost is heavy sometimes. It's high for reaching this point. So let's say this way, we were following the easy path, and the easy path did not allow us to visit every place. Okay, then at some point we need to do some more serious hiking, and yeah, we could not. Okay, but by using these cluster algebraic tools, we can just scan and explore the space that we have, and also draw this nice line and connection between them. Okay, so what we find in particular is that there is this O1 which has 10 vanishing cross ratio, which is a bit special. It's in the middle, and it will always be special. And around it we have this how do you say, annulus of whatever, ring, a ring of origins from 2 to 9, and O10 is in white, so you cannot see it. It's we don't know where it is. We don't know what O10 is. O10, if you go back to the table, is a guy which has 4 vanishing V's, and that seems to be too special in a way, perhaps for for us. Okay, so what do we do with this rosa? So here you see we have this very nice figure, and I spoiled it by putting my TBA patches on it. So these are just the saddle we were using, and as you can see, the saddle sometimes find 1, sometimes find more, like a line, and sometimes find like a surface connecting a few origin, but it's not capturing everything. Okay, again, perhaps we need to play this wall crossing. Perhaps we need to be more, I don't know, use more sophisticated technique. We've tried a few things and we understood that we don't understand. So we stopped. But we could make a marginal conjecture, which is a kind of global conjecture. That is that this Gaussian behavior should hold everywhere it can. Okay, so the color should not matter here, and we should have this behavior we expect on every face of this figure and on every line, as soon as it is connecting, you know, origin of the same kind, which mean here with the same number of cross ratio vanishing. Okay, what it means in particular is that we should have like some 3-dimensional domain where the amplitude vanish. So if you look at the top of this figure, there is a sort of complicated region with two light blue, 2 dark blue, 2 purple, and 2 brown, which is actually a cube. It's not, yeah, exactly this region here, yeah. This is actually a cube, and we expect that the amplitude is vanishing, yeah, exactly. No, not vanishing, sorry, but purely logarithmic on this cube, okay? So we could not do much with TBA, but we could use more standard techniques like perturbation theory to test this conjecture, and that's what we've done and what is described on the next slide, where we use, for instance, Simon's symbol to check that the amplitude vanish everywhere on this ring, and it has to be so if it is just a quadratic in logs. Otherwise, it means there is more than that. But we found that it's also not so between the red spot in the middle, which again has 10 vanishing cross ratios, and its nearest neighbor that has 9. So there, it's not true. And we can do even better than that. We could play some sort of baby amplitude function bootstrap, where we kind of write the general ansatz, which has the property we want, here in the case at hand to be Gaussian. And we kind of write it piecewise because we don't expect it to take exactly the same form everywhere, but which is such that it respects all the symmetry on every domain, that it is consistent with amplitude constraint like the last entry condition, and also continuity. And by doing that, we found that there is just one object which has all the property and as many free coefficients as we expect, which in the case at hand mean as many coefficients as we have roots in the string integrand. So in a sense, the answer is fixed everywhere as soon as we know it at one point, and we do know it at one point with one of our saddles. So we can extend it everywhere. We can globalize it in a way. That's what we could do. Okay, well, there are many open problems. Like for instance, this O10, we don't know where it is. This O1, I haven't said anything about it. But it is related to this more symmetric origin that Pedro had in mind. And there is this question about whether are we really using TBA to its full extent, or are we just making a too light use of it, and so on. So if I have 5 more minutes, but I don't want to abuse of your time because I started late.
Yeah, sure.
Yeah, I do have them. Thanks a lot. I will then briefly mention another game we play, which is connected to this O1, which is a null limit of amplitude, where mimicking, if you can go to the next slide, Pedro. we're mimicking in a way a consideration that people had in for correlators. We decided to send systematically, all the U's to 0 and keep the remaining V's to be V's and W's to be fixed. So that means it's like in the figure here for the octagon. So we set all distances, nearest neighbor distances to 0, and the other one to be of order 1. So in this case, it's not super degenerate because we are left with a few cross ratio in principle in the end to play with. So it's not the point. We do expect to find some object with some freedom, and with in general 2n minus 15 letters left. Okay. But for the hexagon, there is nothing left. For the heptagon, it's not applicable because in general we don't expect this limit to be. We don't expect to be able to reach this limit for odd polygons. But for the octagon, we are precisely landing on a line which is interpolating between two images of this O1 that we had in our classification, with all the U being zeros, and with two V's going to 0, depending here on the value of the parameter, V being 0 or 1. Okay. So if we solve this problem for the null limit of the octagon, we will also get some data about this O1 that was missing before. So as I say, it's very similar to what people are doing for correlation function. In the case of correlation function, it's degenerating into light-like Wilson loops. Here we don't really know what it means to play this game. Well, perhaps it is factorizing into something, but we don't know what the resulting object is. It will be cool if it was some sort of correlator, because then it will be closing the loop, yes. But we have no evidence for that. Of course, it has no reason a priori to be some correlator. Nonetheless, we may formulate a couple of conjectures. Like the first conjecture that one may want to formulate is the fact that we will still have something that is Gaussian and logarithmic, which is a singular part, which depend on the U's. But there might also be a linear part, which will depend on the U and V's, for instance. And then a finite part, which in principle can be very complicated and related to whatever resulting object we have in the end. Which and the second part of the conjecture would be that we can calculate this singular part by using the very same type of formula that we had before. Okay, but here we need another saddle. We need a new saddle because the TBS saddle we've tried were giving us different origin, not this one. So we need to find another saddle, and this saddle we can find by playing with, for instance, a regular octagon, which is a family of octagons that intersect this null limit. It is approaching along a diagonal, but it is going through this this line for a particular value of V, which is 1/2, which has to be so because it has to be totally cyclic. And from there, for instance, we could draw some conclusion about the Y function pattern. So for the octagon, so we have 9Y, and we convince ourselves then that a few of them should be large, a few of them should be small, but there should also be one that is a medium, which is just of order 1 and capturing some V dependence. Okay. So we see it's a different pattern than the one we had before, because now there is a row, for instance, where we exact two Y functions at the same time. So it's not a large phi limit, in fact. If we take large phi, we introduce an asymmetry between the top and the bottom of the row, while here, clearly, we are pushing two of the Y function to infinity at the same speed. So it's actually not a large phi limit. It's something different. And for this reason, we don't expect it to be equivalent to what we had before. Okay. But we can linearize it anyway. We ignore what is small. We also put aside what is order 1 because it's nonlinear, and we calculate our integrand, our string integrand for this saddle. Okay, and the answer is on the next slide. We get this this rational function of z, which now has root at 8 power of unity, which is more or less, I guess, what you would have expected for a regular polygon. Yes, you would believe that it should have something to do with z to the n equal 1, which is what we are finding here for the octagon. And actually, the U part of the problem is extremely nice. It's just given by this formula again with a factorized form and some sum of the log U inside it. Okay. So we did check of it, and it seems to be as good as what we had before. We did check at weak coupling. We also did some check along the line because we have this V dependence, and at two loops. And we were actually surprised to find that there is no need for that there is no non-trivial function of V showing up at this order. So we have Simon symbol. Some people can integrate it, like Lance and Andy and so on. And but there is no non-trivial piece here. It looks like everything is logarithmic. So, and it's captured by our singular part. Perhaps it's an accident, or maybe it's hinting that there is no non-trivial piece left behind. What is sure is that there is a lot of puzzle with this limit, and I will be concluding with that. This is the last slide, which is that actually what specificity of this object is that there is a pole at z equal 1, and this pole is in fact telling us that the Fourier transform is not defined at all, or not defined. It's not well defined, okay? Because you should not have singularity on the real axis. Otherwise, the integral that you started from is not convergent. And that is a problem, of course, for the string analysis, because it's what should we do exactly? Maybe we should subtract something first. Maybe we should improve. I don't know, that could produce extra stuff. That's also a practical problem because the residue at this point at z equal 1, which corresponds to alpha equal pi over 2 in our case, is one loop exact. It's just 4g squared. And 4g squared is something we like at weak coupling, maybe, but it's certainly not something we like at strong coupling. So to have a coefficient that is one loop exact is not good in a theory where you should match some string theory data at strong coupling. So clearly something is going on with this pole, and we don't really know if we should take it, or I don't know, maybe switch to a different prescription. And we don't have the resolution. It's a puzzle. But it seems actually that there is it could be an order of limit issue, and something similar was seen for the null correlators, if I remember well. There was also a piece of it that was one loop exact and did not find a match at strong coupling. So maybe it is of a similar type here. Maybe we have a subtlety that we will have to resolve at some point.
Can I ask a question? So this limit, is it? Can I think of it that you take 8 points, right? And then you flatten so that you get a square. But then on top of that, inside the square, the impurities on the square, they are also null from each other, right?
Yes.
Now, the first limit where you flatten and you get a square with 4 impurities, it was something we did, right? With you and Amit when we were studying the mirrorless matrix, right? Mm-hmm. Because it's like you put at each side, right? You put one excitation, physical go to physical, and one mirror go to mirror, and you get. So can I interpret this limit as a particular case of that, where is it a limit that is dominated by some mirrorless matrix interaction?
It's hard to tell because the first step, what you've done was
so if you don't mind, I'll scroll up. So yeah, I had in mind
it's just the collinear limit, yes. So you are just doing the collinear flattening. What might happen is that you know this SOP parameterization is a bit subtle. If you do things sequentially, usually you don't land at the same place. So if you first do, for instance, send 4 U's to 0 and keep the other one to be 1 or to be a further 1, and then send them to 0, you might not land on the same. Yeah, you might not be at the same place.
So I cannot first put some excitation on the blue lines and then make the excitations null from each other.
Well, let's say this way. It's not immediately clear to me that this is. It's tempting to think along this line, and possibly there is an interpretation like that. That would be interesting to see, like indeed insertion on a square, and then taking the like limit. But okay, we haven't tried, and okay, I will have to check. It's something that looks subtle to me, at least.
Okay, thank you. over here.
Yeah,
right?
but that's more or less it. I have nothing else to say except that okay, we have this formula and it was fun to play with it. Thanks.
Thank you very much for the very nice talk. So let's
Sorry for the delay.
And yeah, are there more questions?
I have a question. So if we were to try to approach this null polygon story from OPE, what we'll do is start with correlators, right? And then we make this null perimeter, and then we make contact with the Wilson loops. And there I could see that we could also approach this limit in many ways by taking OPE limits of this correlator in different orders, right? I can first take 1, 2 to be null, then 3, 4 to be null, then 5, 6 to be null, or I can take different orders of nullness to build the null perimeter.
Mm-hmm.
Could this then, could these various ways of approaching these null limits, do you see any sign that the counting that you have of origins can be interpreted, that you can count how many origins you have by number of ways of making OPs of the external points?
I don't see it, no. At least in the way we do it is very algebraic. But I can't really tell, yeah. I don't know if, for instance, if this cluster algebraic construction could shed some light on this or not. But it does encode a lot of information in the end, surprisingly. I mean, it was a surprise to me that, but yeah, I cannot tell. It's not obvious to me at least, but could be, yeah.
Yeah, it's beautiful. Thank you.
More questions? So I have one. Could you say a few words about how the cluster algebra enters the story and how you built these rosas?
Yeah, I won't be able to say much. It's not my science, but okay. I could say one thing though, which is that I wish we could understand this picture from the Y system side. That's a comment, because there are some connection between cluster algebra and Y system, which are known and which were used, for instance, to prove conjecture, like the Marginal periodicity conjecture for some system. So possibly there is a link, but we could not find it. But otherwise, the way I understand it is that, you know, this cluster algebra, it's a nice way of parameterizing and putting a system of coordinate on your kinematical space, or at least a particular region of it, which is this so-called positive domain, positive region, and its compactification in some sort of big polytop. And what is nice about it is that it's not only just giving you one system of coordinate, which may start from one particular point. Like, for instance, one of our origin could be the origin of the system of coordinate, and then you could move away from it by changing the value of this cluster coordinate. But it's also giving you, you know, some algebraic relation that allows you to change the point of view. So you can change the origin and move to another point, which is nearby, I would say, and will serve as a new origin for your system of coordinate. And this way you can move in the space, in the kinematical space, and at each step, you know, have some nice set of coordinates that parameterize the geometry around, and encode also the jump to the next point or origin in this system.
Sorry, Ben, just a precision. Isn't that very analogous to what James and Omer are using for these OPE computations, where they use the Steinman relations and the symmetry allows you exactly to move, in your language, moving between origins probably?
So what I'm saying is definitely in principle the same as what James and company are doing, and that's because this is the same technique. I'm just probably explaining it very badly in my language or my understanding, but I don't know, perhaps Lance, if Lance wants to.
Maybe.
It would be a more professional answer.
Yeah, I don't know if I have too much more to add. We don't really use, I mean, in the story that James and Omer have been doing, there's this cluster adjacency, which, I mean, we have a slightly different picture of it where we have these causality-based or inspired extended Steinman relations, but they're not really playing a big role in this octagon story. We're not using sort of the cluster adjacency restrictions on the symbol.
Yeah, exactly, Lance.
In fact, as Benjamin was saying, the symbol vanishes everywhere in this diagram, except for the line between O1 and O2. I mean, we do use the symbol to get some perturbative information because we lift off of this diagram to regions where the symbol doesn't vanish. And then we have something non-trivial to complete to a function in that region. But we don't actually use the cluster adjacency because it's also, we do it for the remainder function for convenience here, and it's sort of scrambled. The cluster adjacency is not very, is scrambled up at the level of the remainder function. So we're definitely using the cluster parameterizations, but we're not using some of the other aspects that have been used in other cluster algebra applications.
Yeah, exactly.
But having these parameterizations allows us to do the sort of weak coupling analysis at other points besides the ones that we could get to from the phi sigma tau parameterization that Benjamin discussed.
So let me ask, I think a question that might be related. So you took these cross ratios, the geometrical ones, to go to special values like 0, right? And but the y functions, these ratios of brackets, right, of twisters that are not geometrical points but are also nice cross ratios, would they be also natural to look for origins where those cross ratios go to 0? The ones that are not geometric, like made out of one twister, right? Instead of distances, like one twister of one edge and 3 twisters far away. That they appear even in the 6-point function, right? They appear naturally. They resolve the square roots and they get rid of all this ugly stuff. And so sometimes these cross ratios are more natural than.
Well, we haven't seen in these, at 6 points, we can go out to 7 loops and look for nice exponentials of quadratic stuff. And this, that origin where the cross ratios go to 0 is the only place we really found it. I mean, I should say that those y variable, the small y variables, not to be confused with the TBA variables that Pedro is talking about, when they go to 0, the u's go to 0 too. There's a little bit of a Z2 ambiguity because the y's have transform under parity, whereas the cross ratios are parity even. So there's really 2 hexagon origins there, but they're related by parity. So, and when we look at the MHV amplitude, it's parity even, so it doesn't really matter. And in fact, Benjamin's shown a sort of truncated version of this graph. There's a bigger one where you take more things into account in the cluster algebra, including the parity, distinguish origins of different parity, and different rates of approach. And so you can make a more complicated looking version of this graph. But as far as we can tell, this captures most of what you need for at least the weak coupling analysis.
Yeah, in some situation. Oh, sorry.
No, go. Okay, maybe let me ask because I think it might be related. So, and Ben, you mentioned that it would be nice to understand this cluster algebra from the Y system. I actually thought when you were explaining the first time that this was how you derived this picture. So this would be taking Y functions and, for example, shifting them in spectral parameter, and this describes another solution, but it's the same Y function, and in this way you would relate the various nodes. Is this how you are thinking?
Well, actually, it could be something like that. Of course, if you shift all the way at the same time, you just move from one period to another. Yeah, you're just doing some cyclic shift. That's what I understood. You know, originally when people were introducing this finite time evolution from the Y system, they were trying to prove periodicity or this kind of thing. So eventually you want to prove indeed that the Y system that you wrote, for instance, has the right periodicity to describe an amplitude with a given cyclicity.
Yes. No, of course, what I say does make sense. Yeah. Because if you shift everyone, the area is invariant. You want to relate different areas.
Yeah, you're just moving, but then you could ask, okay, what if I shift one and not the other, include some relative shift? And that becomes more interesting. And possibly that might be the most basic move we need to explore this rosace or this web. But I should say at some point I confused myself in this analysis, and I'm not entirely sure I understand when exactly I am allowed or not to believe that the approximation we are doing is correct or not. It's getting a bit confusing to me when I don't have, this, how to say, link to the OPE, and I cannot anchor it on something that I think I understand physically. So, but that's possibly the way to go for understanding this entire picture and have a uniform treatment from the Y system to get away from, to break free from the OPE. But that's not going to be me, Here in France, we have a restriction. We cannot move farther, like 10 kilometers away from home. So
that's almost over.
Yeah, so okay, maybe during the summer I will explore more.
Is there one last official question? Okay, then maybe let's thank Benjamin again.
Thank you.
Thank you very much. Yeah, okay, we can continue informally.